today, Dr. Cody Powell. He is currently an assistant professor in chemical engineering at the University of Utah. Previously, prior to that, he got his bachelor's degree at the University of Utah in chemical engineering, and then he went to UU. And then he went to the University of Texas at Austin to get his PhD in chemical engineering. So I've already told him I'm an Aggie, so we'll have our disagreement after the seminar. So now he's an assistant professor in chemical engineering at the University of Utah. So he's kind of come back to the West here. He specializes in design, automation, and real-time optimization of complex energy systems, including solar thermal power, combined heat and power, distributed energy systems, manufacturing energy systems, conventional thermal power generation, and automation of energy systems. So he's got quite a bit of experience in this thermal energy complex systems analysis, also the management of those systems. He's also the director of the Intermountain Industrial Assessment Center, also the IEC. We have an IEC here, and so it's kind of a neat little partnership between the two organizations. And he also had some industry experience where he worked at ExxonMobil in previous life, specializing in advanced control and real-time optimization of energy systems as well. So he has a lot to tell about that subject. So please, let's welcome Dr. Cody Powell.
Thank you very much, Dr. Plumley. I'm really happy to be here. And he mentioned I did my undergraduate degree at the University of Utah. So Dr. Leidy, your dean, was one of my professors and has had a huge impact in my career. She's coached me. Even several years after I graduated, I'd call her up and ask her for career advice, and she's always willing to help. When we heard that she was, as a faculty member, when I heard that she was not coming back to the University of Utah, it was painful. It was. You're very lucky to have her.
Everybody here may not agree with that.
You will all the time. But so our loss is your gain. Very happy to be here. My talk today is going to focus on synergistic solar hybrid. So I'm showing you a parabolic trough solar power plant. So when you think of solar power, you probably typically think of photovoltaic panels that you put on your roof. So this is an entirely different concept where you use sunlight to create heat and use that heat to run more conventional steam cycles. So as a chemical engineer, I actually have an adjunct appointment in mechanical engineering, and a lot of my research is really focused more mechanical engineering in nature. So from that point of view, there's just a lot more going on thermally and system-wise. So this is an interesting system that I've had the privilege of studying. Dr. Plumley covered a little bit about my background. So I'm just starting my third year. So the research results I present today we're still just really getting started on this stuff. There's still some of them are just preliminary. We're still working out some details and some kinks, so take that into consideration, but we've made some pretty good progress so far. I was very fortunate to work at ExxonMobil, so professionally my job was to model the combined heat and power and distributed energy systems for a very complex petrochemical system, so an oil refinery coupled with various chemical plants. Just on site there, we had the ability to produce about 500 megawatts, so a pretty substantial power plant, and my job was to model that system and to figure out, okay, how is electricity being made? Is it being made efficiently? What do you do with the waste heat? We would use that to make steam, so how is the steam being distributed and natural gas, and trying to get all of those various pieces of a very complex system to work together harmoniously in a way that made ExxonMobil more money. So now, as a professor, my mission is a little bit different. I want to do research and I want to help disseminate knowledge. So my research focuses in several areas. I mentioned I'll be talking today about solar thermal power. That's what's in bold. I also have students working in other areas like how energy systems interface with the smart grid. So how do you put a lot of different components into a system in a way, and how do you design and operate that system so that some global optima is achieved. Combined heat and power is something that's very interesting. We've actually got, for one of my projects, we have developed software where we are tying into the University of Utah's campus utilities. So we have this live data stream. We have thermal energy storage on campus that we use to shift when we're using electricity. So we have some machine learning based forecasting models to predict how much energy the campus is going to use over the next 24 hours. And then our software tries to optimize, okay, when do you charge, when do you discharge from the storage? Doing some things in conventional power generation with using, again, a machine learning approach to learn how inputs for a coal-fired power plant, there are about 100 different operator-defined inputs to that system. So we're trying to use machine learning to figure out what combination of all those different inputs will lead to minimal NOx production. And we've teamed up with a software company and I actually have a student who works in the power plant and who messes around with this software and tries to get this live software to provide the best environmental benefit for the power plant. Energy storage is something I'm very big into. I don't talk about it much today, but I find that energy storage is going to be just a huge part of where we're going energy-wise. So solar and wind are very important, but those cause some grid stability issues because people aren't necessarily using energy proportional to the way the sun is producing energy. So that creates a lot of what a control engineer would call disturbances to the system. So how do you try and predict when those things are going to happen and use a smarter system with storage to make sure everything is stable and robust? And finally, doing some things in smart manufacturing. And I have some slides at the end of my talk if you're interested in hearing about these other topics. I have like 1 or 2 slides on each of those things if you have questions about it. But the main theme of my research is energy systems. So taking all these different parts of a system and trying to put them together in the best way and make them operate in the best way, at least as far as we can determine. So we try and make a system that has this synergy. All right, so people love solar energy, and I do too. It's a great thing. But when you compare solar energy, at least qualitatively, to fossil fuels, these are kind of pros and cons in each different area. So solar is obviously emission-free, and that's kind of the main thing it has going for it, where fossil fuels produce greenhouse gases. However, solar is intermittent, so you can't control when it's available. Whereas a fuel, a fuel is basically stored energy. You can burn it whenever you need it, and as human beings and as a culture, we've kind of overlooked what a nice commodity that is to just be able to crank up a power plant right when you need the energy. So everywhere where it's bold, that category sort of wins. So solar, there's no fuel cost, whereas with the fossil fuels, you actually have to put a lot of work into getting that fuel out of the ground and getting it in the right state where you can put it into a power plant. Solar energy is sustainable, so as long as the sun is shining, we're going to have this great resource, whereas fossil fuel, depending on who you talk to, one day it's going to run out. It might be several hundred years from now, but one day we're going to have to get off of fossil fuel. Solar actually, one of its big disadvantages is it has a really low energy density. So despite all this sunlight hitting the earth, to actually harvest that requires a whole lot of land area. Fossil fuels, it's pretty remarkable how far a gallon of gas will get you and your couple of ton vehicle. Solar is kind of an up-and-coming technology. We still haven't worked out all the kinks and the bugs with what's the best way to get it on the grid. At small scale, it's okay because it doesn't have that big of an impact. But when you start thinking about really high penetrations of solar and wind, we don't have the technology or the controls figured out to make this whole system operate in a robust way. So that's what I consider to be a very important area of research. And my research focuses on trying to forecast what's coming in the future and try and use that to inform how do I run my system for the next several hours or several days so that it stays reliable and efficient. Whereas fossil fuels are definitely commercially proven. We've been relying on them for over 100 years now in pretty complex ways. I'm showing here some data from the EIA, that's the Energy Information Agency. This is their energy outlook. I think this is now a couple of years old, but they're showing several different electricity producing technologies, so conventional coal, nuclear, solar thermal, and natural gas combined cycle. They have more than this, but I sort of picked and chose the ones that I wanted to highlight. So this is their capacity factor. Basically, you build a plant to produce 100 megawatts, what percentage of that over time do you actually produce? So solar thermal is only at 20% because you build a plant that produces 100 megawatts, you may only average 20 megawatts because at nighttime or if there's clouds, you don't produce anything. So that capacity factor is a big issue. This other metric is the levelized cost of electricity. So this is a term that lumps all the different costs associated with producing electricity into one number. So it takes into account the capital costs of the plant. So while solar energy may be free, you still have to make a big investment to put those panels on your roof or to build a power plant to harvest solar energy. So it takes into account all those costs and annualizes them, and it takes into account fuel cost and the cost to pay people to run your power plant for you. So you'll notice this solar thermal is definitely sticks out like a sore thumb compared to all these other what are called dispatchable technologies, or technologies where you can just start a reaction or burn a fuel and it's just available on demand. So solar thermal, the LCOE for solar thermal is $240 per megawatt hour. So you probably, as much as you might love solar, you probably don't want to pay that much to turn on your TV or turn on your lights. You'd much rather pay this natural gas combined cycle cost of $75. So the objective of this research here, and one of the central hypotheses of what I'm trying to do, is if we combined these two and if we could try and pick and choose some of the benefits of each and merge them in a way that's smart from a design point of view, and if we can operate the plant in a way that's smart from an operational point of view, we hope to drive down the cost of solar thermal power so it's much more like natural gas combined cycle or natural gas fired power generation. So that's what's motivating this. We don't think that we're going to get this lower than natural gas or to have a higher capacity factor, but we think there's going to be some medium in between these two things where solar power, or maybe it might become worth it one day because it's sustainable and emission free. So maybe one day in the future it might be worth it to invest in solar thermal power without subsidies. Okay, so some of the benefits of hybridization. So solar thermal power, and one of the benefits of solar thermal power, period, is that it shares traits with conventional power. I showed on that previous slide, conventional power has been around for decades, and we, as engineers and scientists, we know how to run a power plant. We know how all that works. So solar thermal power lets you tap into really proven technology. You can also share equipment. You can build a plant so that you can have just a single steam turbine or set of steam turbines that could be run by solar or could be run by a fossil fuel. So you have a combined reduced capital cost because those two pieces of equipment can share some infrastructure. You also get this addition of a dispatchable fuel, so something that you're able to fire up on demand. So even though there might be some variability in the sun, you can have this extra source of energy that lets you mitigate some of the issues that come with solar power. This is something I'm really into, is flexibility. So this is becoming a pretty important term when you're talking about regulating the grid, is can your system be flexible? So in the past several decades, when we've built this nationwide infrastructure relying on fossil fuels, we haven't worried as much about flexibility. We need more power, let's build another power plant. Oh, we need more, let's build another one. So we've kind of used this brute force approach. But now with solar and wind, we're trying to adapt the approach so that we run the system smarter. We don't just do bigger and bigger, but we try and do smarter and smarter. So having a fossil fuel in addition to a solar power plant gives you this extra flexibility. And in my world, when I hear the word flexibility, that means degrees of freedom. So if you've done degrees of freedom when you're solving systems of simultaneous equations, if you have 10 variables and 5 equations, that means you have 5 degrees of freedom. So as an optimization person, I can take those extra 5 variables and I can try and find what's the best combination of those 5 variables that gives me some optimal result. So that's sort of very basic optimization theory. So our research goals are to design plants that have multiple energy inputs, like solar thermal and fossil fuels, that are reliable, flexible, and efficient. And my approach, especially as a controls person, is I really focus on the dynamics of the plant. So the models we develop first what are called first principles models, where we're actually looking at heat transfer relations and thermodynamic relations and other physical relationships to build these dynamic models so that we know how the plant is going to operate even when it's going through a change. And that's important because we want to figure out the right automation to couple with this plant. So then we want to use optimization to maximize these synergies. So we want to design a system that is synergistic, but then we also want to use the flexibility that we've built into our plant to apply smart automation so that we can exploit that flexibility. And finally, we want to develop concepts for transition plants. So while we're tapping into fossil fuel technology, we ultimately want to design a plant that you can gradually add more solar energy to and make it more sustainable over the years. So a very common paradigm is that combustible fuels and solar compete, and I think that's a false dichotomy. So I think they should complement each other, and I'll talk about that. Hopefully you'll get the gist of that by the time I'm done speaking today. So there is a review paper that I wrote, and there's been some other review papers where they define levels of hybridization. So combining two different types of energy into a single plant. So what's defined as a light hybrid system would share minimal infrastructure. So the assets, you can operate one almost independently of the other. Maybe the only place where they actually share infrastructure is at the grid level. So you have a solar plant over here, and then 300 miles away you have a coal-fired power plant over here. I'm abusing this term a little bit, but you could think of that as a hybrid system where the combination of those two is feeding energy into a grid, and that's what meets consumers' needs. So obviously the system is much more complex than that, and there are people using energy in a lot of different places, and that gets really complex. But if you think of that as a hybrid, it's pretty light and a weak hybrid. So a medium hybrid would share some major equipment. The solar component is there just to lightly supplement a fossil component. So typically this would have less than 10% of what's called a solar share, or what percentage of your energy comes from solar. So an example of this might be if you have a coal-fired power plant or a natural gas-fired power plant, you might use solar energy to preheat the feed water, and that probably wouldn't be a really critical functionality of the plant. It could probably get by without that, but you could offset some of the fuel usage by adding a little bit of heat from solar. And finally, strong hybrids would share major pieces of equipment. So the solar and fossil components are really tightly integrated. Typically, this would be defined as something that has a 30% or higher solar share, and I'll share some examples as throughout this talk. So this is the plant. This is my student Khalid's work. He has been working on this for a couple of years, so we're still really getting into this. I have a background in modeling the solar part of the process, and what he's done is he's worked on modeling this whole combustion part of the process. So again, this is a dynamic model. We feed into it the total amount of solar energy you're getting, and then we have some flexibility in the system. We can ramp up and down the firing in the primary firebox. So we use this solar heat transfer fluid. This is typically some kind of synthetic oil. It runs through this parabolic trough, just like the picture I showed on my title slide. So you run this fluid through this trough, and these are really hundreds of acres and lots of troughs in series and parallel, but I'm just representing it with a single one. So you heat up that fluid. It gets up to about 400 degrees Celsius. That's sort of the upper operating limit of the fluid itself before it starts to degrade. So when you take that fluid, you run it into a steam drum. So you're making steam with this solar power, and then that that thermal fluid, as it comes out of there, is still at a sufficient temperature where you can do some preheating with it. So our system is designed with some special features. As I mentioned, the primary firebox. This is used to produce steam. When you don't have solar power, you can crank up the gas in the firebox, and you can provide steam generation heat here. One of the issues with solar power, particularly with this parabolic trough setup, is that 400 degrees Celsius really isn't all that hot, and most plants are designed to just run your cycle with 400 degrees Celsius as the maximum operating temperature. Who's familiar with the Carnot cycle? That principle? So the efficiency. I'm glad that Christian is.
Everybody raising their hand.
So the basic principle is your cycle will be more efficient with a higher temperature in it. So these plants by themselves tend to be on the less efficient side because the maximum temperature is 400 degrees C. So what we've done, one of the synergies we've built into this system is that we use this secondary firebox to boost the steam temperature. So we're generating steam at a little bit below 400 degrees Celsius, and then we can fire this extra firing here in this what we call the secondary firebox. So that provides heat for superheating and reheating. And then we have our turbines in series here. We've gone to really great lengths to really model the system well. It's been We use software called Simulink, which is an extension of MATLAB. It gives you a nice graphical user interface where you can model one component, and behind that component you can write all the complex code you want. But then if you want to write code for a different component, you can put that in a different box. So your model can be very complex, but then you have all these blocks that simplify life. Whenever anyone looks at my students' Simulink model, I think they have suicidal thoughts immediately. They just don't want, it's really complex, really just kind of a beast. A lot of that's due to his own organizational style, but this is a very complex model. It's taken a lot of time to get this up and running and to add controllers to it. So one of our objectives is to maximize what we're calling the solar to electric efficiency. So it gets pretty tricky to define even something as simple as an efficiency. With natural gas by itself, it's pretty easy. It's how much power do you produce over the total amount of energy that you're putting in by burning natural gas. With solar, it's pretty easy too. How much power do you produce by how much sun is hitting your field? But then when you combine them, you have to come up with some mathematical tricks to figure out. This is a synergistic system, so it's not as easy to decouple those definitions. But we define something as the solar to electric efficiency, which is basically the marginal efficiency that you're getting by adding solar to a natural gas system. So its mathematical definition is solar power, it's total system power minus the power produced by natural gas, which is we just use a nominal efficiency for natural gas. So we're not cheating there. We're using the normal natural gas power plant efficiency. So we're subtracting off what you would produce by natural gas and then dividing that by the total solar energy hitting your field. So for a typical parabolic trough power plant, that is typically in the area of 15 to 18%. So that's sort of the standard. We're trying to beat that. But you have to think about that solar to electric efficiency as the marginal efficiency you're getting by adding solar to your system. So this is a dual source boiler, which gives us some of that flexibility, those degrees of freedom that we can use to optimize. We have this solar and natural gas steam generation, so that provides some reliability to our system. We can make steam by solar or by firing natural gas. Then this superheating thing, I mentioned the Carnot cycle. Adding that natural gas lets us to use a lot of solar energy, but we still are able to get a high overall cycle efficiency because we give ourselves the ability to fire up this secondary firebox and boost our steam temperature. So we've done put a lot of thought into how we're recovering that heat and how we're getting our boiler feed order up to temperature. And then the control issues, the automation issues are very important in this type of a system because it's not just a natural gas power plant that you can just turn on the gas and it's just going to run at a pretty smooth operation. It's a plant that has to transition from solar mode during the day to natural gas mode at night. So getting that whole system all working harmoniously is pretty non-trivial. So this is a block diagram of what our control system looks like. I won't go too much into it, but we use the flow rate of that fluid through the solar field to control temperature, and we do a little bit of predictive control, nothing too fancy there. Then we have our total power is controlled by turning on that natural gas in the primary firebox. So when the sun comes up, that primary firing goes down to pretty close to zero. Then we use, when you're in solar mode, that's actually when you have to turn on that secondary firebox more, because now your heat's coming from solar, you don't have all this waste heat from natural gas to take advantage of. So this is needed primarily when you're in solar mode and that primary firebox is idle, because you no longer have that waste heat in your convective heating section, which is where the superheating and reheating are done. So we use the reheater to maximize energy extraction. That's a pretty common thermodynamic principle. And then for this study, we're focusing on the design, but our approach is to use detailed dynamic models in this system so that we're not just designing equipment, but we're trying to figure out the controls that go with it and how is one component going to change dynamically and how do the other components respond to that. So just to show you, these are some of the results, just kind of testing out the control system to make sure it works. So this variable here is direct normal irradiance. So this is basically how much solar is hitting your field. So going from 400 to 500 just instantaneously, because this is a model, we can do things like that. So this is a pretty extreme and fast disturbance to our system. But you can see our control system, while it does affect all these other things like our heat transfer fluid temperature, our total power output, our reheater and superheater temperatures, and our economizer temperature, you can see the control system, given this disturbance, it still brings everything back down to its set point within about half an hour, and those deviations are fairly small. These are what some of the results look like when you're actually looking at a real day when we give this actual solar irradiance data for a day. So the power, there are some benefits to ramping up the power to help accommodate some of that solar heat during the day. So we ramp up from 100 megawatts up to about 140 megawatts during the solar hours. That also roughly coincides with grid demand to some extent. So this plant has a little bit of what's called peaking capability. And then we have power production from a high pressure, intermediate pressure, and low pressure turbine, and those all kind of go up and down correspondingly. I mentioned the firing. So here's the gas firing in the primary firebox and the gas firing in the secondary firebox. So you can see that the primary firebox backs down when there's solar, and then the secondary firebox ramps up so it can provide that superheating and reheating heat. So we're getting solar shares that aren't above that 30%, but this is still what I would consider to be a very strong hybrid plant because it's so tightly integrated. So these are some of the monthly performance metrics from the plant. So we get sort of left the nitty-gritty details of the modeling out of this presentation, but if you would like more insight into the approach and what equations we use, I'd be happy to chat with you offline or in here if you have the question. So naturally, the solar fraction, which is an interchangeable term with solar share, that gets a lot higher in the summer months, and then in the winter months you're going to be operating more in the natural gas mode. The solar to electric efficiency is actually fairly constant, and the overall efficiency of the plant is pretty minimally impacted. The solar part actually brings down the average on overall plant efficiency. So during those summer months when you're getting solar, just because of the way we've defined the overall plant efficiency, it does take a little bit of a hit, but it is this sustainable, freely available resource once you've already made that capital investment of building a plant. So here's the annual performance. So we've run our simulations for a whole calendar year so that we can see how does this thing really perform over time. So we compared our metrics to, we have our hybrid plant here. This is a solar power plant by itself. This is another version of the model where we've removed the natural gas and put in storage. So we're getting about that same solar electric efficiency that's typical of a parabolic shock power plant. And then our fuel-only power plant we've thrown in for comparison. So we really want to highlight what are the benefits of hybridizing. So we have a decent solar share, so it's about 16%. The capacity factor, which isn't shown, is a lot higher than the capacity factor for a solar-only power plant, which again is about 20%. We're getting up to, I think, about 76% capacity factor with our plant. So the really important takeaway from this part of the talk is that by hybridizing, by making this synergistic design, we're actually able to improve the solar to electric efficiency by 60%. So if you build a solar power plant by itself, you get the solar to electric efficiency of 15%. And when you hybridize, because you're taking advantage of these different synergies, you're actually improving that to about 25%. So by being willing to combine solar with a fossil fuel, you're actually making the solar power plant perform better. So, this is basically what I just said. So adding solar and fossil fuel, considering them to be synergistic and complementary rather than competitive, you actually recover more solar heat than you would with solar power by itself. So hybridization at the plant level can be very beneficial. So this is that strong solar hybrid, whereas at the grid level, where you just have a solar plant here and a fossil fuel plant over here, I'm going to call that a grid level power plant here in a moment. So the second part of this study, which we've just submitted for publication, is kind of a simplistic scenario where we're just assuming that you want to meet some demand by either natural gas by itself or by solar and natural gas together at the grid level, i.e. building two separate power plants, or meeting that demand with this synergistic hybridized plant. So So these are the definitions we've come up with for this paper. Grid level hybridization versus plant level hybridization. So just keep that in your mind. Plant level hybridization means this synergistic design where they're sharing a lot of equipment and they're really tightly coupled together. So this is a day in the winter. I think this is a day in January. So we're just showing, here's the total demand. So we've made both systems capable of following a load, which is variable. And we're showing here on the grid level power plant, you get solar that comes up, you don't really get that much. This is a day in January, so you don't get a ton of solar power out of it. And that allows the natural gas power plant to back down by a corresponding amount. So it's a little bit subtle here. So our hybrid solar power plant produces this much, and you'd want to be looking at area under the curve, under this black dashed line. So there's a little bit more area under the curve here on a winter day. So when we moved to spring, I think this was a day in March that my student simulated. Same kind of a thing, you produce a little bit of power here, you're doing some good with the solar, but here the area under this curve is a lot bigger. We're producing a lot more power from solar, which means we don't have to use nearly as much from natural gas, and we can back our natural gas power plant down. One of the things we're working on is smoothing out the control here. That's kind of an issue still. All right, but when we look at a summer day, again, that solar power plant has storage. You didn't really see the effective storage in the previous two scenarios because you didn't have enough solar power to really need the storage. But in this case, on a summer day, I think this was in July, you fill up your storage and you can run sort of solar. But by operating with the synergistic hybrid, you can see how much more solar energy we're producing here. So we're getting a lot more power on a July day by having this synergistic design, where we're using the benefits of natural gas to make the solar part of the power plant more efficient. So one of the questions we get asked is, what about the economics? I certainly talked about economics on my first slide. That's important. As much as I love solar power, I also love being cheap and not paying too much for electricity. So you're going to have to make this economical somehow. So we've done an economic analysis coupled with this study for is it better economically to hybridize or to have two standalone plants. So looking at our annualized capital costs, where the natural gas plant would be about 27 million. And again, this is per year. That's not the total price you pay for the plant. This is per year with a 7% interest rate over 30 years. So to build two power plants separately would cost you nearly double that. But if you were to build a synergistic hybrid plant, you can do that for only about $10 million per year more. So that's because you only have to buy one set of turbines, you only have to build one boiler, you don't have to build two separate systems entirely. So once you've lumped in fuel costs and operation and maintenance, this number actually includes the fuel cost in it. You see that the total annualized cost to run the natural gas plant by itself is about 37 million. To do the two separate power plants to meet those same demands is 62 million, and then to do this plant level hybridization is right in the middle, but a little bit closer to natural gas than it is to building two power plants separately. All right, again, the results from that on performance. So actually, let me go back. I want to point out the synergy here is in reduced capital costs. By sharing equipment, you can build a cheaper power plant relative to building a solar power plant by itself. All right, and now these are some of the performance metrics from this particular study. The numbers are a little bit different here because the scenario is a little bit different. The first results I showed were just base load power generation, but now we're actually doing load following with our system. So the results are a little bit different, but still right in the same ballpark. So for the solar fraction, I'll start there, or the solar share. With this grid level hybrid system, you're getting a solar share of about 12%. But when you hybridize, you boost that up to 20%. So a pretty substantial increase in how much solar energy you're getting from your plant. The efficiency has a similar increase, so going from 14.7% up to 26%. The overall efficiency of the system, it does decrease a little bit, as I mentioned, because solar just brings down the average, but it's sustainable, clean solar power, so it's not really a fair comparison. We're just using the metrics that are commonly used. So here's probably the most important number from this study is the levelized cost of electricity production. So I showed you that first slide with the EIA's numbers. Ours are in that same ballpark. For a natural gas plant alone, we get $60 per megawatt hour. Then if you were to build the two plants separately, you're getting $99 a megawatt hour, so about 50% higher. But then to hybridize and to build the plants as an integrated combination, it's about $75 per megawatt hour. So again, a little bit closer to natural gas by itself than it is to building both plants separately. We've done some sensitivity analysis just to try and figure out, okay, well, our plant still doesn't beat natural gas by itself, so what would it take to get there? So we've looked at, well, would increases in the natural gas price be enough to justify this? Once the fuel gets so expensive, does saving that amount of fuel make the solar more competitive? So I don't know how familiar you are with natural gas prices. I think they're in the range of $3 to $4 per million BTU right now. So that break-even point, I'm plotting LCOE here on the y-axis, that break-even point isn't until about $25 per million BTU. So that's about getting close to 10 times more expensive than natural gas currently is. So that's probably a long way off. Natural gas price by itself probably won't justify solar power, but you can see that this plant-level hybrid does become economical a lot more quickly than solar by itself, or the grid-level hybridized plant. So another thing we've looked at is, and a common policy mechanism for the federal government and other government entities is to offset the capital cost. If you build a solar power plant, we'll subsidize some percentage of it. Historically, I think that has been about 30%. So we're looking at what percentage of the capital cost would need to be covered. And again, for the hybrid plant, that gets up to about 50%. So at about a 50% subsidy of the capital cost, and this is just the government offsetting 50% of the solar part of the plant. So it does break even with natural gas at that point, so it needs some help. Another policy mechanism is a carbon tax. So a carbon tax of about, I think that's about $110 per ton of CO2 produced would make our plant more economical. But you can see in every case, the combination of the two plants doesn't ever reach that break-even point. Even with some incredible subsidies, you'd almost have to pay people more than their plant actually cost in order to offset. So one of the takeaways from this slide is, by itself, even the hybridized plant isn't quite there yet. So there's still more technology and development that needs to be done. Natural gas price by itself does not look good at all. We need 10 times higher natural gas prices to justify it. But the renewable energy credit could be something that might be realistic in the future. There will need to be significant changes in the economic drivers before this really reaches grid parity. So the plant level hybrid is much closer to being competitive, but we've also completely discounted any technological advancements that might happen along the way. So I'm certainly working on ways to make this cheaper. So hybridizing itself, we've shown, would make this a lot cheaper to do, but there's a lot of research in building better components that perform better, that are cheaper. So there's still a lot of hope for this technology, but it's going to have to require technology enhancements, which is why this is a research problem and why we're doing this, is to try and figure out how to make this work. Okay, so one of the things that we're working on, this is a grant I just submitted, and I'm glad it hasn't been rejected before I give this talk. But I should hear back about it sometime in September. This is another concept with potential to have a higher solar share because it's a power tower based system. So that parabolic trough that I showed you is what's known as a linear concentrator. You're concentrating sunlight from a wide aperture onto a line. A power tower is what's known as a point concentrator. So you're taking a huge area, like all these mirrors here, and concentrating that all onto one single focal point. So because of that higher concentration ratio, you can reach much higher temperatures. So typically about 560 degrees Celsius is normal. So remember, for the parabolic trough plant, that was about 400 degrees Celsius. So that boost in temperature will help improve our cycle efficiency. There's a different fluid here that's able to withstand those higher temperatures. So the concept that we're introducing and we'll be exploring is a plant that is adaptable. I mentioned flexibility in a plant. If you can open up more degrees of freedom and have different things to do with your plant, you can solve for the best condition by using optimization techniques. So the flexibility that we're building into this plant, I'll get to on our next slide, but you notice we have the ability to produce heat and deliver it here to a solar superheater. So this can have a higher solar fraction because now you can do the steam superheating with solar if you have enough energy available. We still have backup superheating with natural gas. We can also do solar steam generation, but notice we've designed this plant to give us the ability to bypass the solar superheater if we need to, and I'll get to that in a moment. And finally, we can bypass both of those entirely and do this low temperature bypass, and I'll talk about why it might be advantageous to do something like that here in a minute. I've been doing this research I started getting interested in concentrated solar power as a graduate student, and I had never actually seen one of these power plants until back in July. Has anyone seen this? This is real. This is very real. So if you ever... Oh, okay. Yeah. So this is actually right off of I-15, Interstate 15. If you're driving from Las Vegas to Los Angeles, you'll pass this. It's right off the side of the freeway. I'm surprised it hasn't caused more accidents because I found myself just staring at these big glowing towers. And I was telling my wife, I gotta take a picture of this while we're driving through. She wasn't taking a good enough picture, so I might have been driving and taking a picture at the same time. Not really. So one of the issues with these power plants is that, well, the way this is controlled for the parabolic trough system or for this system is the plants are built to try and reach a certain temperature. So this 560 degrees C, they treat that as a constant. So when there's not enough solar power and you still want to reach these high temperatures, what you do is you slow down the flow rate of your heat transfer fluid. So you have this fluid going through your receiver here. So what that causes is when there's not much solar power, you have to turn your flow rate way down. That causes what's called stagnation. So now you have this very hot tower and you're not removing a lot of the heat from it with your fluid. So that causes your tower to lose heat by radiation back out to the system. So one of the things we're introducing is something called flexible heat delivery. So we've designed our system. Here's a simplified version of it in these different scenarios. We want to design a system that lets you collect solar heat at optimal temperatures. So when you have a really sunny day, you collect heat at a high temperature and you run it just like it was designed to do. So you do superheating, steam generation, and preheating. But maybe it's going to be a marginally cloudy day, or maybe you're doing this mid-morning or mid-afternoon, or you're getting some clouds. You could collect heat at a lower temperature. So what that does is it reduces the temperature of your tower. So you're losing less heat to the atmosphere by radiation, and you're cycling more fluid through. You're capturing more of that heat to deliver to your power cycle. But you can no longer reach the high temperatures required for the steam cycle, so you bypass the superheater and you rely on your natural gas system to do the superheating for you. So you're going to lose a lot less heat by operating this way. And finally, if it's winter, if it's a pretty cloudy day, you might not be able to do much more with that heat than just do the boiler feed water preheat. So this is another way of building in flexibility into our system. So the high temperatures lead to stagnation. We want to be able to optimally divert heat to the right place based on the conditions. So we will consider storage in this case. You'll notice that the plant has storage tanks that you can collect heat at these different temperatures, and think of this more as a dynamic transient problem. So we want to forecast prices or solar energy availability or demand or all of those things, figure out how do we run our system optimally. At what times of the day are we going to be doing this, and at what times of the day are we going to be doing this, so that some global objective is maximized. So that might be maximizing total profit for the plant, or it might just be getting as much solar power into your system as you can. But we think that we can improve the economics a little bit more. We can push that solar hybrid curve down a little bit more by having a smarter design. So here's the design part of it. The next part of it actually becomes a lot more complicated because we have to get into some pretty sophisticated optimization techniques where we're not just trying to figure out what's the optimal for right now, but we're trying to look forward using smart models to say, okay, what are we doing now? What are we going to be doing 15 minutes from now? What will we be doing 2 hours from now? And have all of that solved in one single optimization problem. That gets very tricky. That's what I spend a lot of my PhD research doing, so I'm kind of chomping at the bit to solve this problem. So conclusions. Synergistic designs lead to better use of solar power. I think it's not the right approach to say we want to switch over to 100% renewable power. I think it's actually smarter to design systems that use the advantages of both fuels, both energy sources in the smartest way that's globally optimal. So in this case, we use natural gas superheating to improve our cycle efficiency, and we did a lot of things with smart heat integration. So solar and hydrocarbons can complement each other. It shouldn't be this paradigm of one versus the other. If we consider them together, we actually get a benefit that overarches the whole system and improves globally the economics and efficiency of the whole system. So that economic study kind of told us what we thought we would see. We thought we would get numbers that were somewhere in between the two power plants, but we were pleased that it's closer to natural gas, a lot closer to natural gas than building two systems separately is. So we still need to have some dramatic CSP cost reductions. I think one of those cost reductions is going to be by optimizing the system, but we'll see how that catches on. So dynamics and control, because solar is so inherently transient, to me, that's critical to the whole thing, is that having a steady state or a simple thermodynamic model just really doesn't capture everything that's happening. You have to be considering what's going to happen over the whole course of a day or multiple days if you really want to capture the effects and do some of these calculations. That's our approach. So coming up is how do we dynamically optimize our whole system by using smarter operation. So we want to be smarter, we want to take advantage of this synergy and use those degrees of freedom. I would like to thank my students. Again, it's still a little weird for me as a professor to show someone else's work. All that work was done mainly by my student Khalid, and I'm just highlighting all my students. We have like my research with synergistic collaboration, we have a pretty synergistic group where we have kind of a common theme through all of our research, so I want to acknowledge all of my students. So they're here. This work is funded by the University of Utah on some startup funds that I have, and also I have various funding sources, but because of the way the research projects all overlap, I'll just acknowledge all of them. I don't think I have time to, these are the slides about some of my other projects. I'm going to skip through those. I would say I'm going to take advantage of the situation, and if you're looking to go to graduate school and do research that's like this, feel free to shoot me an email. I'm always on the lookout for smart, really energetic students, so don't hesitate to shoot me an email, ask questions, or whatever. Anyway, thank you very much for your time.
Thank you, Cody. We have some time for some questions.
Yes?
How come you got away from preheating, like along with the Energizer? You went to a separate system for the solar. Why did you get away from preheating the fluid entering the natural gas burner?
We didn't. I might have misspoken or something at some point. You still do preheating.
Yeah, but it looks like it's done with your overflow from your natural gas. I don't see the solar going through any preheat of the water or the fluid. It's not water, it's fluid. Is there a reason you got away from that paradigm?
Oh, we still do. I'll go back. I don't know. Sorry. Not the most efficient way of doing this.
Need to optimize.
Yeah, unfortunately, I don't know much about that stuff. Okay, so we still do preheating.
Yeah, see, you're going directly into your steam drum with your solar, and in the past, we've seen preheating, like where your economizer is.
Yeah, okay.
So preheat that fluid with the solar before it goes into the steam drum. I'm just curious why, I mean, is there a reason you got away from that?
So that's what's happening here, the solar boiler feed water preheater. So it comes, I might even have trouble following this. It comes to the solar preheater first, and then it goes up to the
Okay,
economizer.
okay.
So we're still
So it
doing
is
that.
part of the system. Okay, I missed
Yeah.
that. Okay.
Yeah, this is a. I struggle to work my way through it sometimes. Yes.
Cody, on this, you said you're using Simulink, or so does that also include the thermodynamics and changing in the solar, to change the input temperature, it changes a bunch of other parameters. So is that already modules you developed, or?
Everything is based on models we've developed, and it's all in Simulink. However, on the thermodynamic cycle, we've cheated a little bit. These have much faster response time. So we use steady state models, and we pretty much have lookup tables to look up steam properties. But this is done live and dynamically. But yeah, we are kind of ignoring the dynamics of the turbines.
Other questions? Yes.
I have a question about the efficiency increase of solar production. Is that coming from the efficiency loss of natural gas that transfers to the solar?
So I think you're asking where does the efficiency gain come from?
Yep.
Okay, so relative to, the main point of efficiency gain is that relative to a normal solar power plant, you would actually have that heat transfer fluid. First it does superheating, then it does steam generation, then it does preheating. So because you're limited to 400 degrees Celsius, you just have a lower cycle efficiency. But we've sort of skipped that preheater and we're going straight to steam generation, relying on natural gas. So it's taking advantage of the higher temperatures that combustion of natural gas can provide to improve our overall cycle efficiency.
So you were talking about how you get more efficiency adding the solar to this, but solar takes up a much larger square footage footprint compared to like a natural gas plant or something. So they'll most likely have to be in a large flat area of some sort, which is probably going to be far away from the city. Have you guys looked at how much efficiency you're losing just getting that energy to the city? And even if it is like possible for like places such in like Japan stuff where like mileage is very costly.
Yeah, that's a great point. And the line losses, we haven't considered the line losses, and those are usually fairly small, but the geographic limitations are important. And I used to have a map when I talked about CSP that sort of shows where this would be viable, and it's typically concentrated in the American Southwest. So it does need to be, it's definitely geography specific. You wouldn't build this in New Jersey or something. You'd build this in the American Southwest. Spain is actually kind of the world leader in concentrated solar power. The hope is that by thinking about plants differently and thinking about hybrid plants, well, you might be able to improve the economics enough if you're relying on lower temperature solar heat that this could become viable, that it could expand that geographical area by a little bit, but that's a very good point you make. We haven't factored in the line losses yet. Yes?
I understand this may not quite your field, but have you looked into the hybridization of not maybe just solar energy in fossil fuels, but other kinds of renewable resources?
Not as much, no.
Okay.
My other research is, there's a lot of different system configurations you can look at. Okay, so this is kind of a big picture project where we wanted to ultimately look at a whole grid level and how does all this operate. This particular slide is made for a concept we're working on where we're using live price profile signals to try and incentivize homeowners to store energy and help the grid. There's lots of different combinations of this stuff, and this is the one particular one we're looking at. We did look at, one of those first papers I referenced was a review paper that we wrote that was hybridizing different fuel sources with solar thermal energy, and I'm sure you could find several review papers on wind or nuclear. So we looked at hybrids of wind with solar thermal, nuclear with solar thermal, coal and natural gas with solar thermal, but that's just the scope of what we're working on right now.
So in this model, they need this group of neighborhood people need to sign up for a particular thing. Otherwise,
Yeah, this is something we're just playing around with right now. My student who just spoke at the EPI conference a couple hours ago He's working on smarter home automation so that homeowners can respond to price signals from the grid. So ultimately, the big picture is, well, what if large concentrations of people are doing this, then the grid could actually use that price signal as a regulatory mechanism, where if they're expecting a lot of solar and they need people to use it, they could send a lower price signal to encourage people to charge batteries or pre-cool their homes or something. So that's the bigger picture we're looking at on this project. But this one's a hard one to get our mind wrapped around. We're still just scratching the surface there. Yes.
One more for me. What is the lifespan of your hybrid power plant compared to like a natural gas or coal power plant?
That's a great question, and we're using in the economic analysis, I think we're using a 30-year lifespan for either. The hybrid plant will have a lot of those same components, and to be honest with you, it's mirrors, so there's not a huge degradation factor like with PV.
I have a quick question.
Yes.
So maybe I misunderstood, but did you say that there wasn't an energy storage in the hybrid one that was plant scale? That you said there was the one with the grid scale, you had the solar plant that did have energy storage,
Yeah.
energy storage, but the other one did not? Is that
Right, yeah.
Have you thought about what the impact of potentially adding storage into that one might be, if any? Maybe it's negated.
What we found, and we haven't done a really detailed study on this, but what we found is there's not much of a driver to have hybridization and storage. It's one or the other. You need that dispatchability unless you start doing predictive things where you're looking out into the future and you can use your storage to provide more of that flexibility. So qualitatively, that's sort of what we found, is that the storage could be good for flexibility so you can optimize your system, but we're not quite there yet.
Okay. So, all right. Other questions? All right. Looks like we're at the end of our time. So thank you, Cody. I appreciate it.
Thank you so much for having me.